Here we go. We are now on lesson 3 of chapter 3, still in polynomials and rational functions. Well, today we're going to talk about power functions, which just basically means any function that has exponents that you recognize, like a 2, a 3, a 4, a 5, whatever, whole numbers. And I suppose you could have powers of fractions too, but I don't think they're going there because that's a different branch. And then we're going to look at the definitions of polynomials, exactly what polynomials are. Okay, so this could be just part 1, but I'm going to see how it plays out if I do the whole video at once. Since this week is sort of a makeup week, and I will only see half of you one time. So here's our objectives. We are going to express square roots of negative numbers. We've already looked at that, but now we're really going to concentrate on looking for multiples of perfect squares. I think I'm missing a word there. So let me add that. Multiples of, pretty sure they wanted us to say, let me take that cleaner. Multiples of perfect squares. Because we've talked about that before. Perfect squares are 4, 9, 16, 25, 36, 49, 64, 81, 100, and it keeps going. These are your basics. Why? 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36, and so forth, all the way to 10 times 10 is 100. What else are we doing? We're going to identify what's a power function. We're going to talk about end behavior. End behavior of power functions. What does that mean? It means as the function goes to the right forever, what is it doing at the end of it? As functions go to the left forever, that means your x's are getting very negative. What are they doing? You will then identifying exactly what a polynomial function is. Once we know we're looking at a polynomial function, then what we'll do is we're going to identify the degree of that polynomial. And what does the leading coefficient say? That leading coefficient is very powerful. It tells us a lot about end behavior. Okay? So I don't think there's a lot of heavy computation. That doesn't mean there isn't things that we can learn. All right. So first part of the lesson starts out with looking at a table of data. You can see that whatever we're looking at, the x values are years and the y values are the population of birds. So it starts out by saying, suppose that a certain species of bird thrives on a small island. The population over the last few years is shown. So we can see that as we started looking at the data in 2009, there was 800 birds. I'm assuming just 800. I don't see where it says in thousands or in hundreds. There were only 800 of this species. And then the next year there was looks like 97 more, and it looks like it's climbing. I see 9 something there. I see 1,000 something. I see 11. So yeah, this population of birds is thriving. It's increasing its population. Then if you read the paragraph, with that data, somebody came up with this function, calling it P of T. It means population at any given time can be represented by this upside, well, it's hard to say upside down, but it is the opposite of a positive there. So in reality, it is upside down, but just pay attention. But that's a third degree. And I said we're going to talk about degrees. Well, the highest power is a 3 because this is t to the first. And then the 800 doesn't have a variable, so we could literally say it's 800 t to the 0. Because t to the 0 means 1, so it doesn't, it exists as a power, it's just a 1, and 800 times 1 is still 800. So anyway, so they come up with that equation, and P of t represents the bird population on the island t years after 2009. So every year up from 2009, we can see it. We can use this model to estimate the maximum bird population and when it will occur. We can also use this model to predict when the bird population will disappear from the island. In this section, we will examine the functions that we can use to estimate and predict the types of changes. We're going to look at some power functions. So instead of all the verbiage that's in our book, I'll give you the definition, and we'll look at some examples. A power function is a function with a single term. When I say single term, the reason that we don't call it a polynomial, because a polynomial has many terms, at least more than one. This only has one term. So in reality, we call it a monomial. Just a little secret. Monomials are polynomials. It's just that it's doesn't have other terms, but they're going to call that a power function. So it's okay. I can live with it. So the term that is the product, this is where it's important. So we're looking at a single term that has a product, which means you're multiplying. What are we multiplying? A real what? A real number. Nothing with I. It's got to be a real number. What are we multiplying it by? Well, and by the way, that real number, we call it a coefficient. It's just a number in front of. We're multiplying it by a variable raised to a fixed real number. So it just means it's a number that is real, that has a variable next to it, and that variable has a number that's a real number. So I guess I take back what I said earlier. Based on that definition, we could be looking at functions that are fractions, because those are real numbers. But I don't see us doing that just yet, but I could be surprised when I start looking at all the examples. Let's look at some power functions. And what I've given you is perhaps a power function that you may have seen before. A equals pi r squared. You've seen that before. That's just your formula for area of a circle. The radius r. The area of a circle is pi. That is a real number. You may not think it is, but it is. It stands for 3.14159, and it keeps on going forever and ever and ever. But we round it a lot of times to 3.14. And when we were in 6th grade, we rounded it to 3, which really is not accurate, but we did it. And we take the radius and we square it. So there's the variable is radius. Pi is a real number times the radius to the second power. Look at V of t. It has to do with a circle as well. It has to do if you had a three-dimensional circle. Like that. Well, it's still going to have a radius there. There's still a radius from the center inside that balloon to the outside. So it becomes volume now. The volume of that balloon is now the real number is 4/3 pi, or 5 pi over 3. That's still a real number. It's just kind of not friendly. Times what? Times the radius. This time it's cubed. Usually volume always implies a third degree of something. Even if you're doing a box, length times width times height, that's a third degree. Okay. And then P of t, I'm trying to remember, that could just be some function called P of t. Could be a population function. Oh, yeah, I know where I got that. I made it up. A population function, this might look familiar to the first slide, negative zero point 0.3 t cubed. That was that population function of the bird species. I just took the one term because that fits the definition of a power function. It's one term. And negative zero point 0.3 is a real number, and t is a variable, and 3 is the power that it's raised to, and it's a real number. All the exponents are real numbers. The 2, the 3, the 3. So here's the definition in your book. A power function is a function that can be represented in the form of f of x equals k times x to the variable of, if I can see it right, p. P is just a real number. K is a real number. X is not a real number. X is the variable. How do I know? It's in here. F of x. That has to be the variable. And what else do we say here? Where k and p are real numbers and k is known as the coefficient. Any number in front of the variable is always called a coefficient. That'd be good for a vocabulary question on a test. Then Q&A. If f of x is 2 to the x a power function, okay, does it meet the definition? Is the coefficient a real number? 2, yes. That's a real number. And is it multiplied by a variable? No. 2 times x would be multiplied by a variable, but 2 to the x is not a coefficient multiplied by a variable. As a matter of fact, let me ask you this. Is the exponent a real number? No, the exponent's not real number. The exponent is the variable. So the answer is no. There's a couple of reasons, but simply just say no. The exponent is not a real number. That works for me. Okay, example 1. This is just to get you exposed to all the different kinds of power functions and what it can look like. And I guess we are going to look at fraction exponents because here we go. F of x equals to 1, called a constant function. It's just a number, remember? Well, how does that fit the definition? Well, that fits the definition because 1 is the coefficient, and the variable x has to be in there where I don't see it. Do you see it? No, but we can write it and put the 0 power. So it's there. So then that makes it a power function. And then next one, f of x equals just plain x. We've had that before. We have called that the identity function before. I think you remember it's one of in the toolkit. It's also a parent function. So my variable is x. That happens to be right there, still the variable x. But remember, the coefficient is a 1. Because if you don't see it, it's there. There's my variable of an x, and there's it to the first power. So that's how that is following the definition. All right, so let's look at f of x equals x squared. We know it as quadratic because it's a second degree. Also in our toolkit, let me write the over on this side equals to, what's the coefficient? a 1. Is that the x's variable? Yes. And well, I don't have to rewrite it. It's all right there. I just added the 1 in front. 1x squared meets the definition. Same thing for cubic. 1x cubed. Now look at this one. This one should be f of x equals 1 over x. If you weren't paying attention a minute ago, pay attention now. I'm going to put a little bit of warning, warning, warning. Pay attention. If you weren't listening to it, you better be reading it if you were watching the captions. Why is that a power function? I do see a 1, but is it multiplied by x? And I know what you're thinking. No, it's not. It's divided by x. Well, multiplying and dividing are inverse operations, so this can be changed to a 1 times an x. And to tell you that the x is in the denominator, negative 1 power. Negative 1 is a real number. Whenever you see anything to a negative exponent, it means throw it downstairs. You learned that a long time ago. So that turns into, change my color. That turns into my 1 over x to the first power. But because it can be written like this, it's legit. So the reciprocal squared that we had in our toolkit just means it's going to look like this, equals to 1 times x to the negative 2 power, using the same logic. All right, now look at the last two. I have a square root, I have a cube root. They're both in our toolkit function. Well, where in the world is the exponent? Glad you asked. I know what you're thinking. We didn't ask. But of course you do want to know, don't you? So that equals to, I don't see any numbers, so I've got to just put in a 1 somewhere. 1, and I need the variable x somewhere. But what would the exponent be that's a real number that creates square root? And it is 1/2 power. I hope you've seen that before. And if you don't believe me, if that works, use your calculator and calculate 4 to the 1/2 power. Should be a 2. Why? Square root of 4 is a 2. So you should not be surprised if we look at the last one here and say, we're looking at, that's called a cube root because inside the radical, I mean, the first one actually had a little invisible 2 in there. But I don't know if I can even, let me zoom in on it a little bit so I can write it, just so you can see what I'm talking about. Inside here is an invisible 2. But we never write it. So it's technically there. So now that you know that there's a number inside, well, what's the number inside cube root? The number inside the cube root is a 3. So I would write this as equal to my 1 times x, just so I can say that the coefficient's of 1, x to the not 1/2, but 1/3. And I don't like how that looks, so let me take it off. 1/3. That's even worse. Third. 1/3 power. So that's just definitions. So looking at all of those, you can go ahead and read this. I hope that if you read all the examples, they come out to the same thing that I was doing. So I'll let you look at those. And this is a try it problem. Which functions are power? Okay. Are any of them power? I know what you're thinking about f of x. Look at, there's one term. Can't write now. One term, two terms. And somebody could say that is not power, but it is, because it's multiplied. So when you multiply it, guess what it turns into? It turns into 2 times the 4 gives me 8. And then you have x squared times x cubed. Well, that just means we keep the x and add the powers, 5. So the answer is yes, that's power. Second one. Is there any way that a x to the 5 can combine with x to the 3? No, they cannot combine. They're not like terms. So if you can't combine the x to the 5, you can't combine it to the x to the 3. You can't combine it to the x. You're adding and subtracting different powers. Each of those are a power function. Now, it is a polynomial, FYI, because there's 3 different terms. But it's not a monomial. You can't make it into a monomial, so this answer is no. So let me write no. How about this bottom one? The top has 2 terms that cannot combine. The bottom has 2 terms that cannot combine. So combining it with division is definitely not going to make it into one term, okay? I know for a fact that x to the 5th divided by x squared becomes an x to the 3rd. And negative 1 divided by that denominator will not go away. So the answer for that one is also going to be the word no. So let's identify. Now we're moving on to end behavior. End behavior means what's happening as we go to the right to infinity. What's happening as I go to the left, negative infinity. Those are our ends. And what do we say? We usually write the problem as, I'll write it, it actually is called a limit. And so these functions are called f of x, g of x, and h of x. I'll just pick, I'll pick h of x. That's this one right here. It's a darker color. So you can see it goes to the right and up, over and over and over and over and over and over. It keeps going over, but it keeps going up. It keeps going over, but it keeps going up, left. So one goes right, one goes left, but they both keep going up. So what we would say, it's actually a limit problem. It's the limit as x approaches infinity of, and I'm doing h of x. That's what it is. As you're going to the, as x approaches infinity. How do we write it? We'll say as x approaches infinity, h of x approaches, how high is it going is what we're asking. It approaches infinity as we go to the right forever. As x goes to the right forever, maybe that's even better to write. As x goes to the right, y goes up. And we could get fancy and say it goes up forever, goes to the right forever. Now how about going left? As x goes left forever, it still goes up. As x goes left forever, left means negative infinity, y's go up. We can talk about it in many different ways. If you understand what we just said, but we do have to look left and right. The answer for all three of those are the same. So just you could rewrite them all with, instead of saying h of x, we could have said p of x and f of x. But I cheated right here. If you notice, I cheated. I used h of x here, but I wanted you to realize h of x just means a y. Just means a y. They all mean the same. So I'm looking at another one. What's happening with this one? This function is called, well, there's three of them. I guess it looked to me like they were just one. But when I look really close, I do see there's three. So let me pick h again. But I could pick g, I could pick f. Does it matter? This time what I would say is, as x goes to infinity, p of x goes to infinity. In English, as x goes right, p of x, which is y, goes up. Let's do the left. We will say, as x goes to negative infinity, p of x goes to negative infinity. So when I talk about x, that's left and right. So obviously, as x goes left forever, the y values goes to down, which is negative infinity. That's what it means. You can replace p of x with f of x or h of x, because they're all doing the same thing. It's three functions on top of each other looking almost the same because their end behavior is identical. And the center of each of those is also the same, so that's why they look the same. Let's see how to, given a power function, f of x equals some k times x to some n, which is an exponent. It even says that, where n has a positive integer. So we are sticking with what I was saying earlier. This is really, we're concentrating not a negative exponent. And we're not using also a fraction either. We're only using integers. Integers are 0, 1, 2, 3, 4, 5, -5, -7, -100. So we're not doing those crazy ones right now. Identify the end behavior. Here's how we do it. Determine whether the power is even or odd. Wow, there's a trick. If we just look at the power and just say, hey, that's an even number, that's an odd number, and decide whether the constant is positive or negative. So there are two things we're looking at. Is the exponent even or odd? Is the number in front positive or negative? Then you'll be able to know the answer because it'll be the same every single time. So let's look at the first example. It says power positive constant k is greater than 0. That means the number in front has to be 1 or bigger. A 1, a 2, a 3, ... It has to be an integer, remember? That's what we were doing. Actually, we just needed to make sure. We could use fractions. It still will come out. However, think about those numbers 1, 2, 3, 4, 5. They're all positive. And we also know here that the exponent is even. That means the exponents are either a 2, a 4, a 6, or an 8, dot, 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 dot. So we're looking at those two things. I wonder if they give me an example here. They didn't. Well, why don't I try to give us an example? What would it look like? An example. I'm just going to do an example. F of x could be a 2, x to the 6. That would be exactly what they're saying. That the first number in front, the coefficient, has to be bigger than 0. Well, I do think the 2 qualifies. The 2 qualifies as bigger than 0. And the exponent has to be even. Well, 6 is definitely even. So when you look at that, you're going to see something here that maybe you weren't thinking about. Notice how both sides go up forever and ever and ever. Just like your friendly neighborhood quadratic that is not upside down. Why? The even power says it's a quadratic. I know that's mind-blowing, but here's what we write. As x goes to negative infinity, that means left, we know f of x, that's our y values, must go up. As x goes to the right forever, our y values must go up. That's my end behavior, both ways, up. How do I know? There's a 6 there, and it's even. If it's even, both sides will go up. That's the way it works. Go next door, and we happen to see, what if the power is odd? Well, if the power is odd and the number in front is still greater than 0, that means positive. That would look like this. Let me write this one out. Let's see, what did I use a minute ago? I did f of x is 2x to the 3. That one will be f of x is 2x to the 5. Okay, so that's mimicking the other side. What's true? The coefficient is still positive. The exponent is now odd. 5 is an odd number. What do we write down? We're going to say to ourselves, as x goes to the left, let me get a marker again. As x goes to the left, that means negative infinity, the y values, f of x, the function, goes, if it's negative, this is the y value, goes down. That means as I go left, it goes down. And if x goes to the right, the function goes up. It'll always do that as long as the exponent is odd and the number in front is not negative. Next one. This time, the number in front is less than 0. That means negative. Negative. So the number in front is negative now. And we're still going to say this column here is that the exponent is still even. So I'm going to take f of x now. We call it a different letter. I can call it f of x again. F of x now, negative 2x to the 4. The exponent is still even, but there's a negative number. So you remember about the upside down parabola? That's what just happened. More important than that, what am I saying? Now with those conditions, as x goes left, the y values goes down. As x goes to the right, the y values go down. Did you see a pattern here so far? What I noticed is that with a positive or negative coefficient in front, if as long as the exponent was an even number, both sides do the same thing. They go up or they both go down. So I'm expecting to see something different when the exponent is odd. So let's do I'm going to go move into the, again, odd power. And since I did 2x to the 5th before, let me do the negative. We'll call it f of x. Negative 2x to the 5. Both are still odd, okay? Difference is the coefficient was positive here, the coefficient is negative here. And look at the picture. Just look at the picture here, that as I go left, as x goes left, the y's go up. As x goes to the right, y's go down. So let's see how we'd write that out. As x goes to negative infinity, that means left, the y values are going positive infinity, that means up. Y's only go up or down. X only goes left and right. So think about that. And then as x goes to infinity, that means to the right, the y values are going to negative infinity. The y's must be going down. Clearly in the picture. Okay, so there's a very good cheat sheet of looking at positive and negative coefficients versus when they're combined with a even or odd power. Identify the end behavior for polynomial functions. And I'm almost pretty confident that they did not put them all in general form, meaning highest power on down, but we'll deal with it. First one says, that one's in general form. You see the 5, the 3, the 1, and the 0, that's the highest powers. That one's a 5th degree term. This one is a 3rd degree term. That's a 1st degree term. And this is my constant, so it's a 0 degree term. All I care about is the 5x to the 4th. Using that, that's my leading term. And I know it's a 4th degree, which means both has to go up or both has to go down. Since there's a leading coefficient is a 5, 5 to the 4th. 5 to the 4th, 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 5 to the That's going to be it's positive 5. It's more important. I don't care that it's a 5. I care that it's positive. It's a positive 5. So that means both go up. So both sides go up. Why do I care? Because we're doing end behavior. If we're doing end behavior, then I need to know this. Okay. If both go up, I'm going to write as x goes to negative infinity, f of x goes to infinity. That means up. What else can I say? As x goes to infinity, that means to the right. Remember, this was left, this is to the right. I know f of x also goes to infinity. Both of them means up. Both of them means up. Next one. F of x is a negative 2x to the 6th. Oh, look at the powers. They're all, that one's in general form. Beautiful. I just care about this one. I care about that. And I know that the leading coefficient is a negative 2. That's important. And then the highest power is 6. That means it's even. Again, they both go up or they both go down. What do? If there's a negative in front, they both go down. Why do I need to know that? Because we're doing end behavior. As x goes to negative infinity, f of x goes to negative infinity. As x goes to the left, the y's values go down. How about the other side? As x goes to the right, that's infinity, f of x still goes down. So again, if it helps you to put some letters there at the beginning, left, right, down, down. Third one. It looks, again, they're all in perfect good order. See the 5, the 4, the 3, the 2, and the 0, x to the 0. That's 1x to the 0, in case you got confused. So all I care about is 3x to the 5. That's all I care about. That's my leading term. So my leading coefficient is a positive 3. That's all I care, that's positive. And the power, it's a 5th degree. So that's odd, guys. If it's odd, that means one side goes up and one side goes down. Since the coefficient is positive, it looks like this. Since the leading is positive, it comes from the bottom. I keep telling you this because if you get this into your head, you'll be an expert. So what will I say? I'm looking at my picture pretty much. As x goes to the left, f of x is going down. As x goes to the right, f of x is going up. You want to superimpose those symbols here? x is going to infinity, means to the right. The y values is going up. This one over here, as x goes to negative, that means left, and the y values went down. Notice the y values, one went up, one went down. Last one. Are they in order? 3, 2, 1, x to the 0. They are in order. So I don't have to do hunting. There they are. There it is. There's my leading term. So my leading coefficient is negative. That's all I really care, that it's negative. But I'll put the 6 just because. And the highest power of that polynomial, that is a 3. That means it's a cubic. It's a third degree. So again, one side goes up, one side goes down. And since it's negative, it goes down from the top. Then somehow it changes and goes down some more. Yes. That's what it does. So how do I write that? As x goes to the left, f of x goes up. As x goes to the right, that's positive infinity, f of x has to go down, negative infinity. I hope you're not just copying, because you're just copying this down. This is all Greek. Now we're doing identifying and behavior. Well, I'm not going to go over this. This is exactly everything that I have been going over. So I don't know how many pictures I have. First picture is just obvious that it's a positive coefficient with the even exponent, so they both have to go up. Okay, so if you graphed it, that's what you would see. The second one, the leading coefficient is negative, but it's going to be still an even power. 6 is still even, so they're both going to go down. A lot of stuff happening in the middle. I mean, don't get me wrong. There's crazy stuff going on in the middle, but I don't care. We're talking about the end behavior. The only way you can tell what's going on in the middle is to be doing a detailed graph. But in reality, I'll probably only ask you to do a detailed graph a couple of times. Next page. What's happening there? Leading coefficient is a positive, but now my exponent is odd. So one side goes up and one side goes down. Do you remember if it's a positive leading, then it has to come from the bottom up. So it does exactly what we were doing. And then the other one is we switch the coefficient to a negative 6. And it's still an odd number power. So all that happens is it falls from the top. But you know, there's crazy things happening in here. I mean, this is kind of crazy to tell. How could you tell it does it? How could you tell that it did that? You can't tell by looking at the equation. You'd have to graph it on a calculator and make sure you zoom in right to see what it really is doing. All right. What are we doing now? Identifying behavior. I don't. This isn't words. You just look at this, and there's no equation. So how do you identify it? Look at the end. What's happening? What happens at this arrow? What is it doing? What is the end behavior at this arrow? What is it doing? I don't need to see any equation. I can look at that and say, as x goes to the left, that means negative numbers, negative infinity, the y values f of x, assuming it's called f, I didn't look at it, f of x must be going down, so that would be negative infinity. The other side, as x goes to the right forever, remember this side is infinity, this side is negative infinity. Going up is infinity, and going down is negative infinity. Whoop, that didn't look good. Surprise. Going down is negative infinity, going up is infinity, going left is negative infinity, going to the right is infinity. As x goes to the infinity, which means right, f of x must be going, and take a look, it's going up. Infinity. So you don't have to be a genius to look at a picture and come up with the end behavior. And that's the problem we had. There's the answers. I think mine looks pretty good. Try it. Okay, try it's on the same page. Again, do you really need help to understand what's happening here and happening here? I think you can do that on your own. Example 7, identify the end behavior. All right, so it's in disguise, guys. You don't know what the highest power is unless you multiply this through. I'll give you a clue, though. If you have an x times an x, you know that's going to, well, that's too big. If you have an x times an x, you know that's going to be x squared. So technically, you could do this without doing all the work. If you understand that x times x will be the highest power inside there, x squared. And an x squared times this leading part here, which is an x squared, that's giving you an x squared times an x squared. That's giving you x to the fourth. That's technically all you need, except for what's the number in front? Well, 1 times 1 is still a 1. So 1 times the negative 3 will give me a negative 3. That's all you need. You don't need to FOIL that out all the way. You can if you want. Since it's all about the leading coefficient, the highest x's will be when x times x becomes an x squared times the other x squared. So if my leading term is negative 3x to the 4, that means the leading coefficient is a negative 3, and the highest power of this polynomial is only going to be a fourth degree, a 4. Then what do I know? I know that both sides could go up or both sides could go down. How do I know? This is even. It has to be that way. Look at the leading coefficient. Negative. So the winner goes to the upside down. Now that I know it looks like this, piece of cake. As x goes to the left forever, f of x must be going to negative infinity. As x goes to the right forever, f of x must be going to negative infinity. Both sides going down. See, both sides going down. And same problem. Let's see. I think it's the same answers. I can't possibly think I could be wrong. But they did all the work. Look at that. They did the foiling. They did the distributing. Got a beautiful there. And I cheated. I taught you to cheat. Sorry. I did. Guilty as charged. Okay. What is the try it? You're on your own. I'll just give you a clue. X times x times x is x cubed. Your job is to figure out what happens to the leading coefficient. Have fun. If anybody comes up to show me their work, extra credit. But don't tell anybody. Don't let anybody know that you're getting extra credit. Next one. Identify local behavior. Okay, back again to characteristics of functions. We did characteristics of quadratics. Now we're going to have, this is a cubic. And so what am I looking at here? I'm looking at a function could still have x-intercepts. And this one has 1, 2, 3 x-intercepts. That means it's probably a third degree equation. X cubed probably is an x cubed because it only has 3 zeros. It could be higher though, because there could be some zeros that are not real. But if I'm only going to use real zeros, then it would be a cubic. And then I see only one y-intercept. Well, there never will be more than one. There'll only be one. And there's another term called turning points. How many times does this function turn? Well, it turns everywhere there's a max or a min. So since this is a local maximum, that's called a turn, and this is down here at the bottom is a local minimum, because it's the bottom of a valley. So it has 2 turns, or 2 turning points, whatever you want to call it. 2 turning points. And they are your max and the min. They are at your max and min. Next picture says, identify the intercepts and turning points of polynomial functions. I'll let you read that on your own. I probably said a lot of the same stuff. This is how to. How to determine the intercepts. Okay. Well, x-intercept is just like before, guys. If you have a polynomial function, you have to set it equal to 0. Then you have to solve. Hopefully we can factor it, because a polynomial could be huge, could be a lot of terms. Could also use a graphing calculator and find the zeros. Now the y-intercept, this is for x-intercepts. For your y-intercept, then do p of 0 is whatever. That will find the y value that crosses. It's the same thing as your quadratic, because your y-intercept occurs when the x value is 0. So somewhere in here is your y-intercept. Somewhere in there. So that's what I'm doing right here. I'm plugging in a 0 for x. What'd they say? Number 1, they said, determine the y-intercept by making x equals to 0. That's what I just said. And then find the corresponding y value. That's what the output means. To find the x-intercepts right here, that means we need to solve for the input values that yield the output of 0. That just means take your function, set it equal to 0, and then solve it. That's what I said too, solve it. Not as easy as that sounds though. So here's example 8. Determine the x-intercepts of this. We're just doing x-intercepts. Good news, good news. Look at f of x. It's factored. So if f of x equals to x minus 2 times x plus 1, x minus 4, that's already factored for you. And I can tell right away that it's the highest power is an x times an x times an x. So just x times x times x is going to happen. That's an x cubed, so it's going to be a cubic. And I can also tell you what the leading coefficient is going to be because there's a 1 in front of each of these x's. So 1 times 1 times 1. So it's going to turn into a positive 1x cubed. So I know the function is going to look like this somehow. Something like that. But anyway, we're finding intercepts, the y and the x-intercept. So to do the y-intercept, I'll do that first. The y-intercept, x has to be 0. So I'm going to do f of 0 will be 0 minus 2, 0 plus 1, 0 minus 4, 0 minus 2 is a negative 2, times 0 plus 1 is a 1, times 0 minus 4 is a negative 4. That turns into a positive 8. So that ordered pair will be x was 0, negative 8. X-intercepts. Well, thank goodness this thing's already factored, because now it's easy to solve, because we're taking f of x, setting it equal to 0. That means x minus 2 times x plus 1 times x minus 4 is set equal to 0. And if it's factored, then we know that x minus 2 could be 0, x plus 1 could be 0, x minus 4 could be 0. So there's 3 possible answers. Why is there 3 possible answers? Because it's a cubic, and a cubic can cross the x-axis 3 times, 3 different x-intercepts. So what is one of them? X is a 2. So that dot goes 1, 2. That would be right here. What's the other one going to be? X equals to a negative 1. That one will be over here. So that would be a dot right here. The other one's going to be add 4 to both sides. X is 4. So it's 1, 2, 3, 4. That dot's going over here. So then if we combine these ordered pairs are, remember, x, the y value is 0. The y value is 0, so 2, 0, negative 1, 0, and then we have the 4, 0. And we have the y-intercept was 0, positive 8. So that's going to be, should need to go a little higher than 1, 2, 3, 4, 5, 6, 7, 8, way up here. So even by looking at that picture, you should realize that this thing has to come from the bottom. From the bottom, go up, has to cross the y-intercept, come back down somewhere. May not come back down exactly there. It could go up higher. Either way, it's got to come back down to hit this one. Then somewhere it's got to come back up to hit that one. So that would be a pretty good rough graph of the problem. So let's go next page and see how we did. Got the same y-intercept. They just didn't list the point as 0, 8. That's fine. And they got the, look at that graph. Notice it went up a little higher. I said it could go higher than that dot. I was right there. There's my x-intercepts, 2, 0, negative 1, 0, and a positive 4, 0. So I did it. And they even gave me the graph as well. So I'm pretty happy. All right. Example 9. Determine the intercept. So we're doing this again. Another problem of the same. Let's do it quicker. Let me find out what happens when x is 0. For those that don't remember, when x is 0, That's my y-intercepts. That's what I'm doing. Y-intercept. X has to be 0. Piece of cake. So if I plug it in here, I'll get 0 to the 4th minus 4, 0 squared, minus 45. So I get, I'm doing f of 0, 0 to the 4th minus 4 times 0 squared minus 45. Well, that goes to 0. 0 plus 4 times 0, 0 is still 0 minus 45, so it's negative 45. So my 0 comma negative 45. This thing really goes down really far. I probably won't be graphing it. I'll just take my word, my vertical, or this is my y-intercept. X-intercepts. This whole thing has to be set equal to 0 to do my x-intercepts. X-intercepts. F of x has to be equal to the x to the 4th minus 4x squared minus 45 set equal to 0. The only way you can solve this is to factor it. And I know that you guys need a lot of practice on factoring. Perhaps we can do a portion of a lesson just on factoring because it is on the TSI. But I know for a fact that to factor this will be 2 terms. We'll come up to that. The reason I know this is because the highest degree is a 4, and then the middle term is half of it. So it's just like a quadratic factoring. And since this is a 1 in front, I know I'm going to have an x to the square times x to the square. Now, how am I going to find out what the numbers are that goes after x squares? Probably this can be really complicated for some, but here's what I'm going to do. Since that's a 1 and this is a 45, negative 45, I'm looking at a negative 45 number and asking myself, what numbers multiply to get a negative 45? One number has to be positive, one has to be negative. So if I say a positive 1 and a negative 45, that would work. But when you add those two together, you will never get a negative 4 with that. You will never get a negative 4. So I need to start with a bit bigger number. What else goes into 45? Well, I know that 9 times 5 is 45. So the interesting thing about a 9 and a 5, if you subtract 5 from 9, you do get a 4. You hear what I just said? 9 minus 5 is a 4. But I don't want a 4. I need the negative 4. So why don't I use the negative on the 9? That gives me a negative 9 plus 5 gives me a negative 4. So these are the two numbers I need. So watch. One of the x squareds gets the negative 9. The other x squared gets the positive 5. This is perfectly factored. You can take my word for it that this, if you did FOIL, I guess I'll just have to show you, and then I'm going to erase it. X squared times x squared is x to the 4th. X squared times 5 is plus 5x squared. Negative 9 times x squared is a negative 9x squared. Then a negative 9 times 5 is a negative 45. That turns into x to the 4th. And there's more negatives than positives, so it becomes, I subtract that, negative 4x squared, bring down the minus 45, set equal to 0. It's the same thing as I have right here. Are you convinced? I hope so, because I'm getting rid of the evidence. That was just a factoring trick. If you want more of that, let me know, and we can do that. Let me get rid of everything. All right, so good enough. So anyway, what do I do with this thing? Well, I say if it's all equal to 0, then x squared minus 9 could be 0. X squared plus 5 could be 0. This means that if I add 9 to both sides, I get x squared equals to 9 by adding 9 to both sides. But I need to know what x is. So I'm going to get rid of the squaring by square rooting both sides. And when you square root both sides, you have two answers, plus or minus. So one of my answers, x, is a 3. The other answer is a negative 3. I do the same thing on the other side. I subtract 5 from both sides. That cancels. That gives me x squared is a negative 5. Well, what happens when you square root this now both sides? That's not a real number. So in a sense, I could have told you, oh, we're going to have 4 zeros. We do have 4 zeros. But they're not 4 x-intercepts because only the negative 3 and the positive 3 are intercepts. This answer is x equals plus or minus the square root of 5. Is just, I could pull out the I and say I times the square root of 5 to get rid of this negative that we've talked about before in complex numbers. Remember? Is an I, but that's not real. That's an imaginary answer. So here are my only 2 x-intercepts. So let's look at the whole picture and see. Oh, I wrote something wrong. No, I didn't. Negative 45 is how far down it goes. That goes down far. So if I was to try to graph this thing, I don't know if they graphed it or not, but holy cow. They had to go all the way down to negative 45 to put a y-intercept. And then one of the x-intercepts is a 3, 1, 2, 3. The other is a negative 1, 2, 3 that way. Since it's a 4th degree, both have to go up or both have to go down. And since there's a positive 1 in front, they both go up. So I can see the picture looking like here it comes falling down from heaven. Here it goes. Boom, boom. Somehow crossing this y-intercept somewhere, and then it's got to go back up. So that's my rough sketch of what that picture. I'm sure if you use a calculator, it's going to have a lot more funny things happening down here in the bottom. I'm probably going to be looking really weird. Wait, yeah, somewhere. Maybe this is going to be down here. I'm just playing around now. Could do something like that. Who knows? Doesn't matter. They weren't asking us to graph it. Let's see what they did. They found they factored it differently than me. Okay, I see what they did. Same thing. You still got the same answers. 3, negative 3, and then this gave no real solutions. I see what they did. They took the x squared minus 9 and wrote it as x plus 3. That's cool. That's cool. Then they graphed it, and yeah, you see the funny stuff happening down here. Told you, funny stuff happening, but that's using a calculator. Hello, I didn't use a calculator. I still had the right idea. There's crazy stuff happening there. I don't use a calculator unless I have to. Another try it. It's a cubic, and I'm going to help you out. I'm going to get you started. Let's find the y-intercept. That means x is 0. So I'm looking for a point with the x is 0, whatever is going to go there. Really quick. F of 0. If you plug a 0 here, that goes away. If you plug a 0 here, that goes away. If you plug a 0 here, that goes away. So it must be 0. 0, 0. I know I cheated. I just used common sense. And, nothing wrong with that. Now, the fact that there's an x in every single term is good news for you, because now that I'm doing the x-intercepts, I need f of x equals to 2x cubed. Why am I doing the whole thing? Minus 6x squared minus 20x to be set equal to 0. Thank goodness that there's an x in every term, because that means I can factor an x out, leaving a 2x squared. Take one of the powers away from the 3, because I pulled out an x, minus a 6x minus a 20 with no x's equal to 0. And if I was smart, and I wasn't smart a second ago, is I could pull out a 2 out of every number. That makes it even easier, so I should have seen that. Pull out a 2 as well. That means divide this by 2, divide this by 2, divide this by 2. That gives me x squared minus 3x minus a 10. Why did I do that? To make it easy to factor the x squared minus 3x minus 10. Okay, so how am I going to factor that? I still have a 2x. Here's what I do. I know I'm going to have two things. I know I'm going to have an x and an x. The problem is, what do I put with the x? I have a 1 here times the negative 10. That's a negative 10. What two numbers multiply to get a negative 10? Well, I'm going to list them all, because there are not that many. There's a minus 1 and a 10. There is a 1 and a negative 10. But those are silly. They don't add up to a negative 3. So let me continue. I have a 2 and a negative 5. I have a negative 2 and a positive 5. Do either of those add up to a negative 3? Bingo, bingo. Those add up to a negative 3. So I have x, that's a positive 2, x minus a 5. Now I have it all factored. So I know for a fact that 2x could be 0, meaning x is 0. I have x plus 2 could be 0. That means x is a negative 2. I have x minus 5 that could be 0. That means x could be a 5. So let's list all those x-intercepts. 0, 0. Because remember, the y value has to be 0 for each one of these. So I have a y value of a 0 for all of them. And the x is a negative 2 here, and the other one, x was a positive 5. There they are. So I found all the intercepts. And I'm not going to... That was a try it, so they're not going to show us anyway. You're going to have to take my word for it. We talked already about turning points. We talked about them, but here's the secret. A polynomial of degree n will have at most n x-intercepts. Those are your zeros. And n minus 1 turning points. Take 1 away from the highest power. So in this case, the one we just did up here, this one is a third degree, so it has 2 turning points. Well, you shouldn't be surprised. It's a cubic, and it's a positive 2, so it does this. So it has to have a turning point here and a turning point here. 2 turning points. So sample 10. Determine the number of x-intercepts and the turning points. They're not asking us to find them, I don't believe. Just determine how many there will be. So look at this here. It's huge. It'd be hard to solve for the x-intercepts. I could not do it by hand, I'll be honest with you. But since the highest power is 10, and this is in order, so it's the first leading term, which is what I want to see anyway, at most 10 real zeros, which means at most 10 x-intercepts. Why at most? There could be less, because remember when we had the imaginary answers? But I could have 10, and it's going to have one less than that. At most 9 turning points. That was easy. I didn't have to do any work. Easy as punch. And guess I didn't put an answer there. Guess, did I? I guess you'll take my word on that answer. Here's try it number 7. When graphing this function, determine the maximum number of x-intercepts and turning points. Well, we're not going to graph it, but not a problem. Are the powers in order? No, they're not. Because there's a 9, there's a 4, there's a 12, there's a 3. They're in crazy orders. They did not put them in order. It's not general form. So you have to go treasure hunting. Where is the leading coefficient? Where is the leading term? Has to be the one with the highest power. There it is. So what does that mean in English for you? That means at most, what is that term? At most, it's a 9, right? At most 9 x-intercepts. The reason you can just say x-intercepts because if they're not real, they won't cross the x-axis. And that when you take 1 away from 9, at most 8 turning points. That's crazy. That would have, can you imagine having 9 zeros? You know, who knows where they are? I'll just try to pretend to find some. 1 here, 1 here, 1 here, 1 here, 1 here. Wow, that thing's going all over the place like a little roller coaster. All right. Example 11. Draw conclusions about a polynomial function from the graph. Okay. What conclusions? I see a beautiful y-intercept there. So that would be 0, 2 could be the y-intercept. I don't know what this number is there, but there's at least, there's 2. There's 2 real x-intercepts. Well, if they're an intercept, of course they're real, right? But what I was really referring to is two real solutions. It could be a quadratic because look at this. They both go the same direction. But there's some crazy stuff coming in here. So I know it's not just an x squared. It could be an x to the 4th. It could be an x to the 6th. It could be an x to the 8. It could be x to the 12. I don't know. If they told me to find it with the smallest degree, I could come up with an equation. But I don't really know. I think that could be 2.5 in there. This looks closer to the -3 than the -2, so I don't know what else they're going to say. I'm curious if they have the answer for it. Did I say enough? I don't know if I said enough, but we'll find out soon enough here. What they say? Well, it's I don't have the answer for it because now we're on try it number 8. Sorry, I told you everything I can tell you. What can we conclude about this polynomial? Okay. It could be a cubic. How do I know? 1, 2, 3 zeros could be a cubic. And what else do I see? I see a y-intercept here. Let me zoom up here. It's somewhere up in here. Looks like 0.6. Looks like 0.6. And I don't know if these x-intercepts look good or not. Let me erase my dots here. They look really, really, really good. They look like, I'm going to call this that 0.6. I'm going to call it 0.6 to be my y-intercept. I'm going to call this one to be -3, is an x-intercept, and this one is a -1, This one I call it a 2, So that's not too bad. I don't know what else they'd want me to do with it, but there's some things there. I have a maximum value up here if they want me to find maximum, and the minimum. These are local, not absolute. 2 turning points. Well, of course, if it's a cubic, could be a cubic, then yeah, I could have 2 turning points. Well, this definitely only has 2 turning points. So this could be a cubic, but remember, it could also be a 5th degree or a 7th degree or a 9th degree. But the lowest it would be is a 3rd degree. And example 12, drawing conclusions. Okay, this one is factored for you. So you can find all your x without the graph. We know that if I plug in, let me do the y-intercept. F of 0 for my y-intercept, y-int, would be a -4 times 0, which you already know what that's going to be, 0, times 0 plus 3 times 0 minus 4. Well, if -4 times 0 is a 0, 0 times anything is going to turn into a 0. So 0, 0 is my y-intercept. X-intercepts happens when f of x is 0. So -4x could be a 0. X plus 3 could be a 0. X minus 4 could be a 0. With that being said, one of my x-intercepts is 0. That would be 0, comma 0, because the y value has to be 0. The y value has to be 0. So for this one, subtract 3 from both sides. X is a -3. That would be a -3, 0. And then this one, x could be a 4. That would be a 4, 0. Those are my x-intercepts. And I know for a fact that x times x times x could be an x cubed. So it could have 2 turning points. I don't know if I have the solution on the next page or not. I do this time. Yay. Okay, there it is. There's my y-intercept 0, 0. There's all the work. There's my 3 x-intercepts. What do they say? The degree is 3. So the graph could have at most 2 turning points. Yeah, they're assuming that it's enough. Try it. I'll leave that one for you. It's not much different. Try it, number 9. And what have I got next? I'm done. So here is your first page of problems that are in the book. Did I give a handout of it yet? I haven't, but I will. But it's here. I don't have to. They're here. What are we doing? You're doing multiples of 3. And I wrote over here, number 3 to number 43, multiples of 3. So that's 48. So it's 3, 6, 9, 12, ... all the way to 48. That is a multiple of 3. So are they all on this page? Of course not. Here's the next page. There's some more there. Here's the next page. And here's the next page. Does that take me to 48 there, somewhere in there? Yeah, that takes me to 48. 48 is right here. That's the last one. I'll try to print those off for you so you'll have them. But they're there. Have a good one, and have a good Thanksgiving, because this is the only lesson we're doing before Thanksgiving.